Hello everyone, welcome to the Mechanism channel. Today our topic is DFMEA, which stands for Design Failure Mode and Effects Analysis. DFMEA, or Design Failure Mode and Effects Analysis, is a systematic and proactive method used to identify, analyze, and mitigate potential failure modes in a product design. Its primary purpose is to prevent design-related issues before they manifest during production or after the product is in use. DFMEA is a core part of risk management in product design and is often used in industries like automotive, aerospace, electronics, and manufacturing, where design reliability and safety are critical. By examining each potential failure mode, DFMEA helps engineers understand the impact of failures and prioritize actions to reduce risks. Key components of DFMEA include 1. Failure mode. The way in which a component or system could fail to meet its design intent, for example, breakage, wear, or leakage. 2. Effect of failure. The impact that failure mode would have on the system, users, or performance, such as loss of function or a safety hazard. 3. Cause of failure. The root cause that could lead to the failure mode, for instance, a material defect or improper use. 4. Severity, or S. A rating of how severe the effect of a failure would be, typically on a scale from 1, meaning no effect, to 10, indicating catastrophic failure. 5. Occurrence, or O. The likelihood of the failure occurring, rated on a scale from 1, which is rare, to 10, which is frequent. 6. Detection, or D. The likelihood of detecting the failure before it reaches the customer, rated from 1, meaning very likely to detect, to 10, meaning difficult to detect. 7. Risk priority, number, or RPN. A score calculated as RPN equals severity times occurrence times detection. Higher RPN values indicate higher risks, helping to prioritize which failure modes to address. The importance of DFMEA is multifaceted. 1. Prevents costly failures. DFMEA helps identify potential failure points in the design phase, reducing the risk of costly recalls, repairs, or redesigns after the product is launched. 2. Improves product reliability. By analyzing potential failure modes and implementing corrective actions, DFMEA enhances the product's durability and performance. 3. Ensures safety. In safety-critical industries like automotive or aerospace, DFMEA plays a crucial role in identifying and mitigating failures that could pose serious risks to human life. 4. Enhances customer satisfaction. Products that are reliable and perform as intended result in higher customer satisfaction, fewer complaints, and better brand reputation. 5. Supports compliance with standards. Many industries require DFMEA as part of compliance with quality standards such as ISO 9001 or ISO TS 16949 in automotive. 6. Prioritizes risk management. By focusing on failure modes with high RPN values, DFMEA ensures that resources are directed towards addressing the most critical risks. The DFMEA process is a structured approach to identify and mitigate potential failures in a design. Let's walk through the steps together. Step 1. Define the scope and objective. Begin by identifying the product or system to be analyzed, including subsystems and components. This initial step sets the stage for a thorough analysis. Step 2. List potential failure modes. For each design element, Brainstorm all the ways in which the design could fail. It's crucial to consider every possible angle here. Step 3. Determine the effects of each failure mode. Analyze the impact of each failure mode on the system, users, and related processes. This helps in understanding the severity of each potential failure. Step 4. Assign severity, occurrence, and detection ratings. Rate each failure mode based on its potential impact, severity, likelihood of occurrence, and ability to detect the failure. These ratings are essential for the next step. Step 5. Calculate the risk priority number, or RPN. Multiply the ratings for severity, occurrence, and detection for each failure mode to calculate the RPN. This number helps in prioritizing the risks. Step 6. Prioritize failure modes for action. Focus on the failure modes with the highest RPNs and take corrective actions to reduce risks. This step ensures that the most critical issues are addressed first. Step 7. Implement and track corrective actions. Implement design improvements or testing methods to address the high-risk failure modes. Recalculate RPNs after changes are made to evaluate the effectiveness of the corrective actions. This ongoing process helps in continually improving the design. And that's the DFMEA process. Each step builds on the previous one, creating a comprehensive approach to risk management in design. Example of DFMEA. Imagine you are designing a smartphone. One of the critical components is the battery. A DFMEA might look like this. Failure mode, battery overheating. Effect: the smartphone could catch fire, causing user injury and property damage. Cause: poor ventilation design or faulty battery cells. Severity: 9. Potential for injury. Occurrence: 6. Moderate likelihood due to known issues in certain battery models. Detection: 4. Can be detected through testing, but not always easily. RPN: severity times occurrence times detection equals 9 times 6 times 4 equals 216. Failure mode: battery drains quickly. Effect: user frustration due to frequent charging, leading to poor product reviews. Cause: inefficient power management or defective battery. Severity: 5. Moderate impact on user experience. Occurrence: 7. High likelihood as seen in previous models. Detection: 3. Easily detectable during testing. RPN: severity times occurrence times detection equals 5 times 7 times 3 equals 105. Failure mode: battery fails to charge. Effect: the smartphone becomes unusable. Cause: faulty charging port or damaged battery connectors. Severity: 8. Device becomes non-functional. Occurrence: 4. Low likelihood due to robust charging technology. Detection: 2. Easy to detect during initial product testing. RPN: severity times occurrence times detection equals 8 times 4 times 2 equals 64. Actions based on DFMEA. 1. Overheating with an RPN of 216. Action: improve battery ventilation. Test batteries under extreme conditions. Reassess. After improvements, the occurrence may drop to 2, reducing the RPN to 72. 2. Quick drain with an RPN of 105. Action: enhance power management software and improve battery quality control. Reassess. Reduced occurrence or detection would lower the RPN. 3. Charging failure with an RPN of 64. Action: ensure robust design of the charging port and connectors. Importance of RPN. By calculating the RPN, teams can focus on the most critical issues, the highest RPN values, and allocate resources to address the most significant risks. For example, in the above analysis, overheating is a high-risk failure mode that requires immediate action, while battery drain and charging issues can be addressed later with medium priority. Conclusion: DFMEA is a powerful tool for identifying and mitigating risks in the product design process. By focusing on potential failure modes, their causes and effects, DFMEA helps ensure a product is reliable, safe, and meets customer expectations. Its ability to prioritize risks using RPN makes it essential for industries where design and safety are critical, such as automotive, electronics, and aerospace. Thanks for watching. Please like, share, and subscribe. Happy learning!